Good day everyone, I'm Jonathan Lozada and I will be discussing vibration control. Vibration control allows engineers to validate the reliability of their products through control testing. Vibration control is the reproduction of equivalent vibration and shock environment experience in the field or in a laboratory. The picture on the right is field vibration, while gathering some data on this profile and then reuse that vibration on a shaker table. So the purpose of the environmental testing is to expose the design flaws of a product in controlled conditions. So we want to reduce the chance of field failure in real-life operating conditions. So during the test, if we break a part, we might ask ourselves, did we overtest the part? If we don't break the part, we ask ourselves if we undertest the part. If we're going to use an established standard, such as like military standard, we have to ask if the standard is relevant to the type of operating condition that the part might actually experience. Oftentimes, people think of vibration testing in terms of military or maritime or aeronautical or space applications. These are some of the more common, well-known types of vibration testing. We can test to reproduce the ones like aircraft takeoff and landing and rocket launch. Vibration testing can be used for every different type of product, including automotive components, small electronics like circuit boards, PCs, disk drives, etc. So really, vibration control testing is applicable to a very wide array of fields. So how do we do this vibration control testing? We'll talk about equipment and a little brief introduction to different test types. So here, what we have is a typical vibration control system. So the typical vibration control system consists of different elements. First, we have is vibration controller. This is used to manage the test and determine the output needed to recreate the desired vibration levels. Then we have data acquisition hardware. And this is used for both acquisition and output. Next is the amplifier. What the amplifier does is it will gain the signal from the front end and input that into the shaker. Then we have the shaker, which is typically either electrodynamic shaker or hydraulic device that has a moving mass to recreate the vibration levels. There are horizontal and vertical shaker tables depending on your test type. So here, we have a couple of different test types covering the frequency range. So depending on the frequency range of the test, different methods might be used. Sign control is good for applications dominated by sine and harmonic content. Examples are helicopters, engines, turbine blade, passage, etc. Often characterized by a profile of frequency versus amplitude over which the shaker performs a sine sweep. Random control is good for products experiencing broadband vibration. Examples are reproducing operational environments, shipping environments, etc. Often characterized by a PSD over a broad range of frequencies. The shaker will output the broadband-shaped vibration. Shock testing is good for products experiencing explosive or collision events. Examples are rocket launch, firing weapons, drop testing, etc. Often characterized by an acceleration versus time waveform which must be produced on the shaker. Now all of these tests are going to be performed in what's called a closed loop control environment. The difference between closed loop and open loop is in both cases we have a target profile, we have a shaker, we have a front end outputting that signal. But in the open loop control, there is no feedback into the shaker. It's just purely outputting the signal and measuring what we're getting. In the closed loop, we're outputting the signal and then we're gonna check if that output is actually matching our profile. And if it's not matching our profile, We'll update the drive signal and then adjust to make sure that our output is matching our desired test profile. Here we have again our control system. Our system transfer function is going to be a measure of the output over the input. The shaker is going to have an input of volts, and the output of the system is going to be the G's of response. That's the end of my presentation. Thank you.